Okay, so today we're going to continue our discussion about the estimators. Last time we stopped at discussing about the relative efficiency, which is a criterion to compare two estimators. We call theta 1 hat and theta 2 hat. They are estimators of the same parameter theta. So here in this example, let's say that we have a random sample, which is composed of NIID random variables from this Poisson distribution. And here the parameter we're interested in estimating is lambda, the Poisson mean. So here we have two estimators. One is the average of all the NIIDs. The other is just the average of the first two IIDs. So in other words, in the second estimator, we only use the first two random variables in our random sample. So then the question is, which one is more efficient? So which estimator is more efficient? Okay. To answer this question, I think we must have some good intuition already. One uses a sample of size n, the other uses a sample of size 2. So intuitively, the larger the sample size, the better the estimator. So to confirm that, we need to first verify both estimators are unbiased, right? This is the condition. When they're both unbiased, then we don't need to compare their bias because they're both 0. Then we just need to compare their variances. That's what we are going to do. So to answer this question, we just need to calculate the variance of each estimator. Okay, so now we should be familiar with the fact that the variance of a sample mean, the average of IIDs, should be equal to the variance of each random variable, which I will just use x1 for representation, because x1 to xn are IID, they share the same variance. So it should be equal to the variance of one random variable divided by the sample size. So this is a fact we should all be familiar with now. And then we know the variance of each xi because it's Poisson lambda, then it's lambda. Okay, so this is the variance for the first estimator. And similarly, for the second estimator, we can just write down this directly because it's also the sample mean, but the sample size is just 2 instead of n. So it's equal to the variance of x1 divided by 2, which is lambda over 2. Okay, and then we know that here we said n is greater than 2. Since n is greater than 2, we have the variance of lambda 1 hat less than the variance of lambda 2 hat. Okay, so hence lambda 1 hat is more efficient because it has the smaller variance. Okay, and so I forgot to write this. Also, the expectation of lambda 1 hat equals to the expectation of lambda 2 hat equals to lambda. So both estimators are unbiased. Okay, so that's what I want to say about the efficiency, which is essentially inversely proportional to the variance of an unbiased estimator. So that concludes this part. And for the next part, I'm going to talk about a question we postponed from the last homework, problem 4b, regarding the distribution of an order statistic. Okay, so this is the topic I will first talk about today, the order statistic. Specifically, we are going to talk about the minimum and the maximum of a random sample. Okay, so the setup is that we denote x1 to xn, as we always do, be IID random variables with CDF, if you recall, it's a cumulative distribution function F, okay? And PDF, probability density function small f. These are the two functions. Okay, and we sort x1 to xm by increasing by an increasing order. Okay, so we put the smallest one first and the largest one last. So with the order, then this is denoted by a parenthesis. Okay, so the parenthesis means it's ordered. And so basically the x parenthesis 1 is defined as the minimum of x1 to xm, while the x parenthesis n is defined as the maximum of x1 to xm. So as now you can see that by this definition, the minimum order statistic is not just depending on one of the random variables, even though it's going to pick one of them as the minimum. However, you can see the definition of the minimum depends on everything, depends on all the x1 to xn, not just a particular xi. Okay, so this is called the first order statistic. And this is called the nth order statistic. Okay. So here the question we are interested in doing is we want to find the CDF and PDF of x1 and xm in parentheses. So we want to find the distribution of each, depending on the IIDs, CDF and PDF. So we're going to use the big F and small f here to help us with the derivation. Okay, so to help you understand what we are talking about here, so let me just quickly show you a PDF I found online. I'm going to share this on CCLE. So what we are talking about here is this case. So let's say that we have n equals to 10. So it's a 10 sample size of 10 random sample. Let's say we draw them uniformly from 0 to 1. So you see, these are the 10 values we draw in one realization. This is the second realization. This is the third realization. So you see, for each realization of the random sample, we can define the minimum. Here it is. This is the minimum in the first realization, minimum in the second realization, minimum in the third realization. And we are denoting these things using the random variable x parenthesis 1. Okay, and then we are interested in is here we pull those 3 realizations here together, and if we do more and more realizations, we can get more dots here, and we want to describe the distribution of those blue dots, which indicate the realizations of the minimum or the first order statistic. Does that make sense? Okay, so this is the intuition behind what we're doing, and so let's come back to the notes. Oops, sorry. Just give me a second. Okay, so coming back to the notes, how can we do this mathematically? You know that you could use computer to help you see the realizations of this x1, right? But how can we give it an analytical formula? So to answer this question, we will start with the definition of the minimum or the CDF. So we'll first do the CDF of the minimum, first order statistic. So to do that, we define its CDF by this big F, and we put the random variable in the subscript just for clarity. So it means, okay, this is the CDF of this X parenthesis 1. And we evaluate the CDF at a real value, small x. By definition, this is defined as the probability that this random variable is less or equal than this constant small x, right? And then what does it mean? It means that the minimum is less or equal than the small x. But knowing this direction is not really helpful because the minimum being less or equal than small x doesn't tell me where the other random variables, like the second smallest, the third smallest random variables, where they are. But if I reverse the direction by doing, by probability, this is equal to 1 minus the probability that the minimum is larger than the constant small x, then I can say more. Because once the minimum is larger than x, it implies that every other random variable is also larger than x, right? So this expression, probability, can be re-expressed as all my NIIDs, x1 is larger than x, up to xn is larger than x. This is the key. So linking the minimum relationship with small x to all the random variables with x. Does that make sense? Okay, and then this is a joint probability for n random variables, and they are IID, independent. So using independent, we can write a joint probability as a product of each random variable's probabilities. So then by the independence, we can write this as 1 minus the product. I goes from 1 to n. The probability that each xi is larger than x, right? And now we know each xi follows CDF f, right? We are going to use this. So xi follows the CDF f. What does this imply? This implies that, I'll just write it, the probability that xi is larger than small x is just equal to 1 minus f at x, okay? And then with this relationship, we can go one more step. This is equal to 1 minus the product, I from 1 to m, 1 minus fx, okay? And because you see in the product, it's basically the same thing that's multiplied for n times. So this is equal to 1 minus fx raised to the power n. So we obtained the CDF of the minimum. Now for the PDF of the minimum, we just use the definition that the PDF is the derivative of the CDF. So we write this as small f. We still denote the random variable in the subscript for clarity. When we evaluate it at a real number, small x, it can be defined as the differentiation of the CDF at this x. Okay, and then we use the chain rule to do the differentiation. And I'll just write down the result. So it turns out to be n times the differentiation of big F is equal to the PDF, small f. So I use that. Or maybe let me just go one more step. For clarity, d dx fx times 1 minus fx raised to the power n minus 1. Okay, I'm getting this by chain rule. And this one is equal to the small f. So n times the small fx times 1 minus fx to the power n minus 1. And note that when I apply the chain rule, I would have a negative sign and the negative sign coming out of the negative f. So these two negative signs got canceled. So that's why I don't have a negative sign here anymore. Okay, so that's the CDF and PDF for the minimum. Do we have questions before we move on to the maximum? Okay, if not, then let's talk about the maximum. The nth order statistic. So I think for those of you who understand the first part, you should be able to this part yourself now. But let's still do this together to confirm that we really understand it. So the CDF of the maximum is defined by definition of the CDF is the probability that the maximum is less or equal than the constant small x. Okay, and now for this probability, we have a lot to say. Since we know the maximum of the random sample is under small x, it means that every random variable is under small x. So we can re-express this probability as x1 less than x up to xn less or equal than x, right? That's what maximum implies. Okay, now we apply the independence to write a joint probability as a product of marginal probabilities. So it's this, right? And then this is actually easier. By the definition of this CDF of each xi, which is f, that's exactly fx. Right? And now it's the same fx multiplied for n times. Okay, so it's basically this. That's the CDF. And then the PDF will be straightforward to take the differentiation of the CDF. Okay. Okay, now I'm going to write down the result directly as the chain rule. By the chain rule, it will be n times the small f at x times the big F at x, now raised to the power n minus 1. Okay, so now we obtain the PDF of the minimum, the first order statistic, and the maximum, the last order statistic. With this, then if you recall, we had an interesting MLE estimator before, right? So let me pull that up. It's about estimating the upper bound of the domain of uniform. So we showed you that in this case, when you do the MLE, the maximizer of the likelihood turns out to be the maximum of x1 to xn. Okay, so using our new notation, what we just defined, this is the x parenthesis n. So therefore, if you want to derive the MLE, right, this is the MLE. It's a different notation. So using this definition of the MLE, if you want to define its bias, then what you need is to calculate expectation of this maximum, right? And then let me just write this one more step. So what I want is that, so for example, in this example, we had x1 to xm, IID from uniform 0 to theta, right? And we have theta hat MLE equal to the maximum. This is what we previously derived. So then, if you want to define the bias of the theta hat MLE, which is what we didn't do in the homework, it will be equal to the expectation of the theta hat MLE minus the true value theta. And for the expectation, now we know its density, right? Let's quickly do it. So what's the density of the theta hat MLE in this case? So the density I'm using this estimator random variable in the subscript to mean its density. So which will go from here, right? From this result. I'll put a star here. By the star, we need, what's the small f for uniform 0 to theta? Actually, it's 1 over theta. Okay, that's the density when x is between 0 and theta. So let me just quickly say it. So it's equal to n times here the density is 1 over theta. And what's the fx? Fx is the CDF. Actually, we can know it's equal to x over theta, okay, raised to the power n minus 1. So I need to say this is for x between 0 and theta. So for such x, I would have the density in this way. Otherwise, for x out of this range, it should be equal to 0. But this is actually making sense since the maximum is based on a random sample from this distribution. Since every value here cannot be larger than theta or less than 0, then the maximum must also be between 0 and theta. So that makes sense. Okay, so then the expectation of this theta hat MLE would just be calculated by the definition of expectation. So I will do expectation from 0 to theta, and x, the value in this interval, times the density for each value in this interval, then integration. Okay, so you can see what is that. So I'm just going to simplify the formula directly. So it's n times 1 over theta times theta to the power n minus 1 x to the power n. So I multiply x into this. So dx. Okay, and let me simplify the terms a little bit more. So I can get n and theta to the power n out of the integration. Inside the integration, I'm just left with xn dx. Okay. So then we know how to do the integration here. So it would actually be n plus 1 times x to the power n plus 1, evaluated at two extremes, 0 and theta. Okay. And then we can see that the result is n over n plus 1 times theta. That's the expectation. Okay, with this, then we can go back to the bias. And the bias of the MLE would be equal to n over n plus 1 times theta minus theta. And it's not 0, but negative 1 over n plus 1 theta. So we have a small negative bias. However, we can see that this bias is going down to 0 as n goes to infinity, right? So the larger the sample size, the smaller the bias. So we can see that this goes to 0 as n goes to infinity. So in this case, we give such an estimator a name, which is called asymptotically unbiased. So this adverb asymptotically means that when the sample size goes to infinity, when n goes to infinity, under that scenario, what happens? And what we're saying is that here the bias is going down to 0. So that's why as n goes to infinity, the estimator becomes unbiased. And that makes sense, right? You see, when you have a small sample size, you cannot expect that the sample would exactly touch the upper bound. So that's why when you take the maximum, you know that the maximum is under theta. But as your sample size gets larger and larger, your values, n values, become denser and denser. So you can better expect that the maximum is going towards theta, right? So that's the intuition behind this result. Does it make sense? Okay, so that's that's this example. And next we are going, and that's all I want to say about the order statistic. So as you can see, the PDF I'm going to share on CCLE. In that one, it has more general result. That is, for any order, say the case order statistic, you can still have a way to calculate CDF and PDF, and that is a little more complicated. You just need some discussion. So like for the case order statistic, for it to be less or equal than an X, you need to consider what's the left of it, what's the right of it, and have the two parts discussed separately. So that's a little more complicated, and it's about combinatorics, but I think the general idea is still quite similar. So the minimum and the maximum are the two easiest ones to discuss. So that's what we presented here. And I think what the focus here is to understand that we can derive the CDF of a random variable based on the definition. And then given the CDF, we can derive the PDF. Okay, so that's it. And another important result I want to give today, because this is an undergraduate class and we have just 1 quarter, so we cannot go into the details for some advanced materials, but I want to give you the result because I think this is a very important result to know. So this is called the MLE theory regarding a nice property about the maximum likelihood estimator. So if you recall the central limit theorem, if you recall, which is something we included in our midterm, right? And also our homework. What this is about, it's about the distribution, or I can say the asymptotic distribution of Xn bar. Okay, the average, or you can say Sn, the sum, because one is just one, this average is 1n of the sum. So recall that in our applications, what we use, right? What we use is this approximate distribution. That is, we said, oh, Xn bar is approximately following normal distribution with mean as the expectation of one random variable. Let me just call it xi, and variance as the variance of x1 divided by n. That's what we did. And for the sum, we can also approximately say that it follows a normal distribution with the mean as n times the expectation of one random variable, and the variance is n times the variance of one random variable, right? So I think now everybody should see this, right? And this, we have used this for multiple times. And if this is still something quite new to you, I would say that probably a review is needed. So yeah, we are going to use this again and again. And I will say definitely in the final exam. So this is a very important result about the application of central limit theorem. But as you can see, as I said, approximately, because here we are still having n as finite, but large, right? Large n result. And it's not really about letting n go to infinity, because even though that's the definition of asymptotics, however, on the right-hand side, you can see I will have trouble if I let n go to infinity. For the top one, if I let n go to infinity, the variance is going to 0, right? When it goes to 0, it's no longer a distribution. It's just a point. It's just a point at the expectation of x1. That's a point mass, we call it. The distribution is concentrated on one value. And for the latter, for the bottom, if I let n go to infinity, you can see both the mean and the variance are going to infinity. And that's not a meaningful distribution, right? So I would say this is what we do in practice. Okay, in practice for large, finite, for large but finite n. For example, n equals to 100. Right, so we do this. But in theory, the rigorous way to write this result is this. We write root n times xn minus expectation of one random variable converges in distribution to normal distribution with mean 0 and the variance of each random variable. So this is the rigorous way of writing the central limit theorem. So you can see what we did is that we multiply root n to the left-hand side. So with the multiplication, we actually can get rid of the dividing n in the variance. So therefore, the variance on the right-hand side is stable. It doesn't depend on n anymore. So it will not shrink to a point mass, or it will not go to infinity in any way. So this one is stable, and we put everything about n to the left-hand side. That's how we define a random variable sequence. And when we say convergence to distribution, I don't give the formal definition here in this class, but you can think about this convergence in distribution as, so on the left-hand side, you have a random variable for every xn, right? So the sequence, so the random variable sequence, let me put here, the random variable sequence changes with n. So for say n equals 1, you are going to have it just as x1 alone, that's the mean, minus ex1. Okay, for n equals 2, you are going to have the average of x1 and x2. Okay, but now you are going to multiply this by root 2. That's the second thing. And for n equals 3 and so on, so for n equals n, then you're going to have this. Okay, and so on. So basically, we are talking about this random variable sequence. We're talking about this random variable sequence, and we are talking about the distribution at each n. And this convergence says is that as your n goes large, then the distribution of the random variable at that n will become more and more like normal random variable that follows this distribution. So that's what we are talking about for convergence in distribution. Okay, so this is the formal definition of central limit theorem. It's about convergence of random variables in the sequence in terms of distribution. So the reason I recall this is because this is very related to what we are going to talk about in terms of the MLE. Okay, so basically, the MLE result, the MLE asymptotics is this. Let me just put down the result for you. So it's also root n, sample size square root, times the MLE, which is our random variable, which is based on a sample of size n, minus the parameter it estimates. This will converge in distribution to normal distribution with mean 0. The variance is 1 over the Fischer information of theta. Okay, so here the MLE estimator is based on a random sample x1 to xm, okay, IID. So that's the setup. So therefore, you can see the similarity between the MLE and the mean. And of course, in most cases, the sample mean is a special case of the MLE. If the parameter theta is the expectation of x1, which we often denoted by mu, right? So in the normal distribution case, we saw that the MLE of mu is actually x and bar. Okay, so with this result, even though we didn't prove it, but I can briefly say that to prove this result, we are going to use something we did very similarly when we define the Fischer information. You recall that the Fischer information is defined as the expectation in two ways. The first way is expectation of the square of the derivative of the log likelihood of theta, right? Given one observation. That's one way to define Fischer information. The second way is that still given that log likelihood of theta with one observation, just 1x, you define the second derivative of it, and then you take expectation, and then you take a negative sign. So that's the second way to define the Fischer information. But either way, you're going to use the negative log likelihood of theta given one observation. So to derive this result, we are going to use the Taylor expansion of that log likelihood. So Taylor expansion is always a way for us to do a lot of things. Here for the Taylor expansion, we are going to go to the second order because the second order will give us a quadratic approximation of a function. And we're going to use that to go to the normal distribution. So that's basically it. And also that, if you recall what we did for the CLT, central limit theorem, how we proved it, if you recall, we used the moment generating function as a tool to show the convergence, right? That the sample mean of the MGF of X and bar is convergent to the MGF of normal, right? That's how we did. And recall that in showing the convergence of the MGF, we also have some small terms. We also use Taylor expansion, and we show that the small terms are going to 0 as n goes to infinity. And that similar idea was also used in proving the MLE theory. So I'll just briefly say that because this is something we actually covered in our PhD level class about asymptotics. So not in this one. But this result is very useful because it can tell you, so in practice, you can use this result to say that, approximately the MLE would follow a normal distribution with mean as the true parameter theta, the variance as 1 over n times Fischer information theta for a large finite n. We have this asymptotic, we have this approximate distribution for it. And you see, why is this so nice? So this is actually telling us asymptotically from the above. First, this theta hat MLE is unbiased, right? Because asymptotically, its mean is just the theta, true value, and achieves the Cramer-Rao CR lower bound, right? In terms of its variance. So you see its asymptotic variance is just 1 over n times information, Fischer information. And that's exactly the Cramer-Rao lower bound, the minimum possible variance that an unbiased estimator can hopefully achieve. So it achieves that. So you can see those two things, realizing this result can give you a very good impression about the MLE. That is, it's a really nice estimator when you have large sample size. Does that make sense? So I would say this result actually establishes the MLE as the to-go estimator for parameter estimation. If you can write down the likelihood and if you can find the MLE, then this is the way to go. So that's why in now most applications, people just go for MLE for a lot of the commonly used models. For example, linear model, which I think you will learn from 100C, you will learn linear regression. And in that case, the parameters you want to estimate will be the coefficients in the or the slope parameter. That's usually what you're most interested in the linear model. And to estimate that, if you assume your error terms follow normal distribution, you can write down the likelihood and you can find the MLE. And in that case, a very interesting result is that the MLE can also be interpreted as the least squares estimator. Okay, so basically MLE will be seen and used again in your future classes. It's just that here we give you the basic introduction. Okay, so this theory, even though we didn't prove it, we actually tell you it establishes the MLE as a very nice estimator, especially when the sample size is large, because here this justification is about the asymptotics. Okay, so any questions? All right, so if not, then we will move on to our next topic, confidence intervals. So how many of you have learned this concept from previous classes? I would assume most of you did, right? Like in stats 10, I think confidence interval and hypothesis testing should have been covered. So now we are going to give you a more mathematical introduction to it from what we learned. So confidence intervals. Even though you may have known how to calculate it and short as CIs, so you may have known how to calculate it from your previous classes, but here what we want to emphasize is the randomness. Okay, what is the randomness? What is this interval actually is? So that's the most important thing about this confidence interval, and this understanding can address a lot of the common confusions or misunderstanding about the CIs. All right, to start with that, we're still going to use what we learned before, an estimator and the parameter. Okay, so I'm going to use the sample mean xn bar as the estimator, the population mean as the parameter to start with. Okay, so let's say that we have, again, x1 to xm, they are IID, okay? And with, for each random variable, let me still use x1 as a representative. I denote this by mu, and the variance of it by sigma square. So we'll use those notations for simplicity. Okay, and we want to use xn bar, the average, as an estimator of mu. Okay, so we just reviewed the CLT, central limit theorem. We're going to apply it. So here, let's say that the question is that we want to find, this is the emphasis, a random interval, such that covers the true parameter mu with 95% probability, okay? So this is the formal definition of a confidence interval. So we call this interval as the 95% confidence interval, CI. So in other words, the interval itself is random, and we wanted to cover the true parameter value, true parameter mu, which sits there unchanged, so that this interval may change. But hopefully this interval will cover that fixed mu with 95% chance. That's what we want. Okay, so how can we find this interval? And we are going to use the estimator, which is itself a random variable. Use that as the basis for constructing a random interval. That's what we want. Okay, so the approach is to use the definition, use the distribution of xn bar and see how this distribution is around mu. Okay, use the distribution of xn bar around mu. Okay, we use central limit theorem to give us the distribution. So CLT says when n is large, we have xn bar follows approximately. So sometimes we just ignore the approximation, just use it, right? Normal distribution with mean mu. So you see mu enters here, variance sigma square over n. So with this, then if we want to say, we want to construct an interval that is around mu, how about this? So let's first look at this probability. So if we look at this probability, let's say we have xn bar following this distribution. Maybe it's better for me to draw the density. Okay, so here mu is right here. And this is the PDF of this normal mu sigma squared over m. This is this distribution. So in other words, I would know that if I can define this interval that covers 95% of the probability under the curve, and because of the distribution is known as this, so actually we know we can write this as mu plus 1.96 times sigma over root m. So we know that it's about 1.96 standard deviation from the mean. And here the standard deviation is just sigma over root m. On the left-hand side by symmetry, it's mu minus 1.96 standard deviation sigma over root m, right? So between this interval, we know this is a nice fact about the normal distribution. Here, the density curve under the curve between those two intervals, that area is 0.95. So this is a fact, we know this. And let's use this fact to say, given x and bar follows this distribution, I would have x and bar between mu minus 1.96 sigma over root m and mu plus 1.96 sigma over root m. This event would hold with probability 0.95. Okay, do we have questions about this? It's just regarding the distribution of x and bar. Okay. However, this interval is not what we want. Okay, the reason is that this interval is not random. It involves mu and sigma. Both are constants, unknown parameters. So not what we want. What we want is an interval that's random and it contains mu. So the approach is that we can actually reorganize the terms. So we want to basically make this inequality by having random variables in the boundary, two boundaries, and put the parameter of interest in the middle. So put mu in the middle. Okay, and the boundaries are random and not involving random, irrelevant to mu. So the boundary cannot involve mu because mu is what we want to cover. So it cannot be in the boundary, it must be in the middle. So to solve that, you just need to find a way to move mu as the center and the boundaries not involving mu. And we can show that this is equivalent to say mu is less or equal than x n bar minus 1.96 sigma over root m, less or equal than x n bar plus 1.96 sigma over root m. So since these two events are completely equivalent to each other, right? So from the right-hand side, you move mu, you move this part to the x n bar. So it becomes x n bar minus 1.96 less or equal than mu. That's what we have here for the left part. From the original left part, we have mu less or equal than x n bar plus 1.96 sigma over. That's what we have for the new right part. So therefore, these two things are completely equivalent. So therefore, for this event, we still can say its probability is 0.95. But now you see we satisfy what we need. The interval is random and what it covers is the true parameter. So you can see that, so this interval x n bar minus 1.96 okay, Okay, this interval is a random interval. Random because x and bar is random. That covers mu with 95% probability. Okay, so it is a 95% CI, confidence interval. So this is the whole logic. But one thing I didn't say is that to make this an interval that is computable, the sigma here is known. We assume it to be known. Okay, otherwise you don't know what's sigma. So let me just make it simpler. This sigma is assumed to be known. Okay, with this, then this is a valid interval. When sigma is not known, okay, that's a more realistic case. We don't know what a sigma is. Then in that case, you can put in an estimator for sigma into the formula. But in that case, to use the estimator with great confidence to say, because we know the estimator cannot be exactly equal to sigma, right? Based on what we discussed. So, but to use that, which we call plug-in, let me just write this. When sigma is unknown, use sigma hat as plug-in. So this is an estimator of sigma. So then the confidence interval would become okay, this is what we'll do. But what I want to say is that this is only a good confidence interval if the sigma hat is really close to sigma. Okay, so its effect, if its deviation from the true sigma doesn't matter that much. And for that, we didn't actually talk too much about it, but I can briefly say that a good sigma hat should be very close to sigma when n is large. Okay, so therefore, when you have a large sample size, then sigma hat is very close to sigma. So you can safely use it in place of sigma. And the formal definition of this is called consistency. It's a consistent estimator. So you can think about consistency as not just unbiased, because unbiased just says that the expectation of sigma hat is equal to sigma. But for a particular realization of sigma hat, it could still be far away from sigma, right? When the variance is big. So consistency says that every realization is getting closer and closer to sigma as n goes to infinity. So it's still an asymptotic result, which we didn't talk about because it involves what we call the convergence in probability. Here, the CLT is just convergence in distribution. So I will try to avoid talking about that in this class because we have other things to talk about. And this is more like a theoretical property instead of practice. So that's why I think if you have this intuition that if we do this plugin, we must have every realization of sigma hat close to sigma, then you know that's good enough. And regarding the confidence interval, right, in your intro class, you would focus on calculation. So in calculation, what you will do is that you will have x1 to xn as n numbers. So based on those n numbers, you compute an average number. So you put the average here and here. That gives you an interval. But based on what we just said, that interval you got is what? Is a realization of this random interval, right? So that's just one particular realization. So therefore, for that particular realization, you actually don't know whether it covers mu or not. It could cover it. It could not cover it, right? So you can just say that I believe the way I construct the confidence interval will give me 95% chance that the realization covers the mu. So in other words, the 95% probability is talking about the way you construct the confidence interval. It's not about that particular interval you realize. I don't know if that makes sense. Because that one realization is, it could be missing it. It could miss it could miss mu, it could cover mu. You only have those two possibilities, right? That you don't know. What you can only say is that the way you construct the interval will give you a pretty good chance, 95% chance that the realization covers mu. Okay, so that, I think that's the biggest confusion people have. So for example, one wrong way to say it is that, okay, let me just continue writing this. Say, given a set of realizations, let's say x1 is say like 0.5 to xn is 1. So you have those n numbers. And the confidence interval, the 95% CI, has realization. I'll just make up the number, 0.25 to 0.75. Let's say this is the interval you realized, okay? So given this interval, how can you say about the mu? What can you say about mu? Okay, so the first mistake one, people say is that mu falls into with 95% probability. This is the first wrong statement many people use, which is wrong because in this statement, what is the random variable? When we say probability, we must pin down what is the random variable. So clearly, this interval is not random anymore because it's just a number, right? It's just two numbers. You're not treating it as random. So the mu becomes the only random possible random variable. But in our whole confidence interval construction, we treated mu as fixed, as an unknown fixed parameter, not a random. So because we are not talking about Bayesian statistics at all in this class. So confidence interval is a frequentist idea. So mu is fixed. So both are fixed. Wrong. Because mu and this interval are both non-random. That's the issue. So we are talking about two fixed quantities. So then there's no possibility, there's no probability. It's just that it belongs to it or it doesn't belong to it. So it's a 0-1 thing instead of a random event. So therefore, so mu is not a random event in frequentist statistics. So later, when you learn about Bayesian statistics, you will consider mu as a random variable, and then that's a different story. And that time, in Bayesian statistics, people don't use the concept confidence interval, they will use credible interval. So as in contrast, but we will not touch that in this class, just for your further information. So that's mistake one. And this is the most common mistake. And the second common mistake, I would say, is that, so maybe I would say it's similar to the first mistake, but just said in a different way. So the second mistake is that we are, so 95% is about is about this particular realization. Actually, it's not. It's about that random interval. Wrong, because 95% is about a random interval. Okay, let's say that here we had this xn bar minus 1.96. It's about this random interval. Okay, and is just one realization of it. So I can make an analogy about what the difference is. So for example, in the analogy, let's say that I have x follows standard normal distribution, right? And one realization, with one realization of this x, with one realization as, let me say, 0.5. When I draw it for once from the standard normal, I got 0.5. So in this case, what I can say is that, so the correct way to say it is that, okay, x falls in the interval minus 1.96 to positive 1.96 with 95% probability. So this is a correct statement, right? It's about this random variable. But the wrong statement is that 0.5 falls in the interval blah, 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 blah. So if I replace x by 0.5, then the statement doesn't hold because 0.5 is already a realization. It's just a number. You cannot say the number belongs to this interval with that probability. So it's an analogy, which says that here in the same meaning, the chance probability is not about the particular realization of this random interval, but it's about this random interval itself. Does that make sense? Okay, I think this is the key misunderstanding maybe you didn't learn from the intro class, and I want to emphasize here. And so that's why I feel like the random variable understanding is crucial to statistics. Otherwise, it just doesn't make sense to talk about probability. Okay, so with this, then the application should be quite straightforward beyond the sample mean, beyond this, right? So before I conclude for this lecture today, we have about 10 minutes. I'm going to talk about like the confidence interval you could do for any parameter theta based on the MLE using the MLE theory that gave us the foundation. Okay, so more generally, so let's say that we have, they are IID, and they are from a PDF density function. We know the density. I left out the argument because they can be any value x I may pick given parameter theta. Okay, this is the more general way of doing it. And we know this form of f. For example, it could be the exponential density function, or it could be the gamma density function. Those are just common examples, or normal density. So then let's say that, just as a quick review of everything we covered, how can we get the MLE? So the MLE is basically defined as the maximizer of possible theta values, the possible theta values that maximize this density function, joint density. So because it's IID, it's basically I put each xi in, and like their product is the joint density of x1 to xn given theta. And often this is difficult to maximize. So we maximize its log form instead. Okay, so it becomes just a summation log fxi theta, right? So this is basically our definition of the likelihood, often written as big L theta. And this is our definition of the log likelihood, which is often written as small L theta. We used those before. Okay, that's how we define the MLE. When you are here, then the next step is often to take the derivative of the log likelihood, set it to 0, right? And solve for the theta value. That's the MLE. Okay, and then the next thing is about that. Now let's say we're interested in constructing the confidence interval for theta given the MLE. So starting from the MLE, because MLE summarizes our data x1 to xn. So it serves as a basis for constructing the random confidence interval. So you can expect that the confidence interval would involve the MLE in its two boundaries with the theta in the middle. That's the thing to be covered. So we know the theory of the MLE, right? The distribution of the MLE, asymptotic distribution of MLE would involve the Fischer information, I theta. So how do we compute that? That's also a question. So regarding the Fischer information, I theta, recall that we define it in two ways. It's either the expectation of the square of this thing. So basically we can just do d theta log f. We can just put 1x in it. Let me just say x1 theta. And here the expectation is with respect to x1, taking the expectation for x1. That's one way to define it. And the second way is to do the negative expectation, d squared d theta square log fx1 theta. Second derivative of the log density or log likelihood for one random variable. Here the expectation is still for x1. Okay, so these two ways are how we can compute the Fischer information. With this, then the MLE distribution tells us, so MLE approximately follows normal distribution with mean theta variance. Okay, so this is when n is large. And what I didn't say is that also the F density needs to be smooth enough. So everything here will hold that in the common distributions like gamma distribution, that smoothness is not a concern. So we just assume it. Okay, so with this, then this gives me the distribution of the MLE, right? So then I can use the normal property again to say that the probability that the random variable MLE falls under the normal mean minus 1.96 times the standard deviation. Here it will be root n times Fischer information theta. And under theta plus 1.96 times the standard deviation, which is 1 over root of n times Fischer information theta. This would be valid, or sorry, probability is 0.95. Yep. So still, we're using that normal distribution property. Given that this random variable follows this normal distribution, then it falls under these two limits, right, with this probability. And the two limits are defined as the normal mean plus minus 1.96 times the normal standard deviation. Here it will be 1 over root n times I theta. Okay, now I need to reorganize the terms to get a confidence interval, right? But now the trouble is here, theta appears in Fischer information. It's not just in the mean, it's also in the Fischer information. That gives us a lot of trouble, right? So how can we make the theta only in the middle? And for many complicated Fischer information formula, you may not be able to do it. So therefore, we just do plugging, okay? So what we aim to do is that first we can write this equivalent to theta hat MLE minus 1.96 less or equal than theta, less or equal than theta hat MLE okay? So this event is exactly equivalent to the previous event. So I just shuffle, I just reorganize the terms, right? To put the theta in the middle. But I'm saying that this is not a confidence interval yet, because this one involves theta, right? These two involves theta. Theta is unknown. So how do we do it? So here the plug-in approach would work. So if we do plug in by replacing the unknown theta in the two boundaries by theta hat MLE, by assuming that the theta hat MLE, when n is large, is very close to theta. So we can replace it. So therefore, we would have the probability that theta hat MLE minus 1.96 divided by root n times, now the Fischer information, I change theta to theta hat MLE. Okay, that's my left boundary. My right boundary is changed in the same way. Okay, now because we do the plug-in, now we can say this is approximately 0.95. So this is by assuming that theta hat MLE is already close to theta. So we do the replacement. And also, I didn't say that the MLE theory says theta hat MLE is a consistent estimator of theta, which means that theta hat MLE would converge in probability to theta as n goes to infinity. But I just didn't introduce that formally. But that guarantees that this approximation is reasonable. So after all, now you can see both boundaries are only about our data, right? With your data, you can compute the two boundaries. It doesn't involve unknown parameters. So we're done. So the conclusion is that theta hat MLE minus 1.96, this, and the other boundary okay, is a 95% confidence interval of theta. That's the conclusion. And this result was obtained by the MLE theory, asymptotic distribution of MLE, coupled with the plug-in approach. Okay, so any questions about what we talked so far? So that will conclude our discussion today. And also I want to say that this 1.96 will change together with the confidence level. So because you see, this is how it comes in, right? Depending on the area we want. Now we want 95%. So therefore, the two limits would just be 1.96 away from the standard deviation away from the mu. But depending on what the level is. So basically, you can see this is what? This is actually, if I make it more general. So basically, if I say I want the level as 1 minus alpha, confidence interval. So for example, alpha is equal to 0.05, then that's 95%. Or alpha could be 0.1, then that's 90%. So if you want to have, this is the mean, okay, this is the mean. If you want to have 1 minus alpha over here in the middle, by symmetry, you have alpha over 2 in the two tails. So in other words, here, how far away you are from the mu. This distance is defined by what? It's defined by basically mu plus, this is the quantile from standard normal. I would say it's just the inverse of the standard normal CDF at alpha over 2, okay, times the standard deviation of this normal. Here, the standard deviation is sigma over root n. So I'm saying that here, this 1.96 is just equal to the inverse of the standard normal at alpha over 2 when alpha is, let me see what, 0.025, right? Because it's 95 in the middle, I have 0.2, I have 0.025 here, 0.025 here. So that's how we can compute it. So essentially that number is just from a quantile of standard normal given the left tail probability. Okay, so playing with the standard normal distribution will give us a lot of useful information about this. And I think that's called a critical value, right? So critical value 1.96 corresponds to 95% confidence interval. And I believe if you change the alpha to 0.1, then it becomes, you get a 90% confidence interval. So when it's 90%, you'll have 5% here, 5% here. So for the 5% left tail, the corresponding quantile from standard normal, I think is about like 1.67 or something. Yeah, so those are just the values we use. But since 95% is the most commonly used level for confidence interval, so that's why I just use 1.96 throughout to simplify that part of discussion. Okay, so I think that's all. That's all I want to say about the confidence intervals. And I'm going to release the next homework with today, so you can start working on it. And so I will try to do a real example in the beginning of my next lecture, so you can get a concrete example about the confidence interval construction calculation. And then we will move on to our next topic, which is about hypothesis testing. I think that will be the last major part of this class. And my plan is that we will do maybe 2 more lectures. So one on Wednesday, one on next Monday, and on the next Wednesday one, I mean the Wednesday of week 10, we are going to do a review lecture so that we will review everything we have covered, especially what we will emphasize on in the final. So the homework, which will be assigned today, will be due on next Monday. So that's the plan. So you still have 1 week to work on the problems. Okay, so thank you, and I'll see you on Wednesday.